So what we're going to do in this one is that we're going to look at cycloalkanes. Same deal, all right? Open chain, but this time they're wrapped in a ring. And the nomenclature is pretty much the same, but when they become a ring, okay, we're introducing two new concepts. Okay, the first one is this idea of isomerism. Remember, last week we talked about conformation. Okay, in a molecule, conformation is posture. Conformation is whether a molecule is opened up like this or whether a molecule is twisted in like this. Okay, stereochemistry is different, but it's also because of the structure. So that's a big concept. Okay, in terms of ring strain, you can look at, make a note. I'm not going to spend too much time on it, but cis-trans isomerism is the biggest one. Okay, and then in terms of ring strain, we're really going to focus on how a 5-membered ring and a 6-membered ring tries to minimize ring strain. Okay. Let's look at the naming. Naming is straightforward, right? Cyclopropane, of course, 3. Cyclobutane, that's easy, isn't it? Let's try you on some couple of things to point out. Okay. The question then becomes, if you've got an alkyl group on a cycloalkane, that's easy, isn't it? You see this is methyl. 1 carbon is a methyl group. There's your methyl, and it's on a 5 ring, so it's methyl cyclopentane. The problem comes then when your chain, okay, and your group, one of them has to be the parent. One of them has to be the dominant one. All right? And a very simple rule is whoever's got the most carbons wins. All right? Not carbon in a chain, but carbon in the whole group. So here, because this has only got 3 carbons, you just call it cyclopropyl. That's easy, isn't it? Yeah. So instead of calling this one butyl cyclopropane, it's the other way around, cyclopropyl butane. Yeah. And of course, if it's in a ring, in terms of supposing here, looking at this one, again, what you want to do is on a ring, remember a circle has no beginning and no end, but in terms of numbering, there has to be a beginning and an end. So where you choose your starting point, very simple rule, just so that all your groups ends up having the lowest number possible. So if you look at this particular one, okay, I could have started with any one of them being carbon number 1, but if I made this carbon number 1, then I would have ethyl at 2 and another methyl at 4. Make sense? Okay. If I were to choose a different one and I say, oh, okay, let's make this methyl number 1, then when I go through, I'll get 1, 2, 3 there and 4 there. You go, well, what's wrong with that? Yeah? What's wrong with that? Look at your number. That's a 3. That's a 2. Yeah. Start anywhere else. Start with the ethyl group. And again, you get locants that are not as low as possible. It's as simple as that. Okay? Best thing to do is try some examples, isn't it? Okay, there you go. Try those. I'm sorry, I'm not going to have time to do all 6 of them. I'm assuming if you looked at the notes, you've looked at this already, okay? So I'm going to go through this fairly quickly. Let's pause. That's right, different arrangement of atoms. Different configuration works, but the broader definition is same molecular formula, different arrangement of atoms, okay? So we have seen, if I had shown you, say, in terms of isomerism, if I had shown you this compound and this compound, clearly the arrangement of atoms are different. You can see it immediately, right? They have different functional groups, very different properties. Okay? Supposing I had shown you, say, something like this, okay? They are the same, aren't they? Because all I've done is I've twisted this bond up, but there's rotation. Okay? So here, They're not isomers. Okay? However, this would be different, and we've discussed this last time. So it's the same molecular formula, same number of carbons, same number of hydrogens, but the arrangement is different. In this case, the difference is very, very pronounced. The difference is breaking off one of these and forcibly moving it onto the middle one. It's a big difference. It's a structural it's a form of structural isomerism. Okay? Stereoisomerism is subtly different. Stereoisomerism, look at this pair. Okay? So you have the molecular formula is the same. The arrangement of atoms, the connectivity is the same. Okay? The order, it's carbon, 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 carbon in a ring, and then with methyl groups coming off two of them. But the spatial, or if you like, stereo arrangement is different. Okay? So what we have here, you see, this ring has a top face and a bottom face. Just like I've got a 6 ring here, right? You see there's a top face and a bottom face. Okay? Now, I haven't got the 3 version for you, but you can see it here. The 2 methyl groups are both on the top face. Yeah? And here, the 2 methyl groups are one on the top face and one on the bottom face. And therefore, you get that isomerism. Okay? Stereoisomerism. It's just like, in the alkenes, you can have an alkene like this. Okay? And an alkene like this, and you've got a cis transform. Agreed? So what is it about the alkenes that makes this form and this form different? What is this top form, cis or trans? Trans, and the bottom one is cis. What makes these 2 forms different? What is it about the alkene that makes those 2 forms different? Yeah, what does the double bond do? Or what doesn't it allow it to do? Doesn't allow it to rotate. And really with a ring, okay, so this is a 6-membered ring, that's the bond, that's not a double bond, is it? Okay, but I can't twist these, you see. If I twist this, the rest of the ring pulls it back. Make sense? So the ring forces this bond to be locked, whereas in an alkene, the double bond, the pi bond, the pi bond here causes that bond to be locked. Okay? In a ring, the rotation is locked because of the ring, and that's why you get cis and trans. Okay? So that idea is fairly simple. Okay? And then this is important, but unfortunately, let's carry on with this. One way to draw this is simply just to draw a triangle, and you see this one here is down. So I'm going to use a wedge. Okay? I know that wedge is angled slightly up, but it's dash. This is a dash. Yeah? I can even draw the dash like this. Yeah? And this dash is pointing up, but because it's a dash, what you're saying is pointing away from you. And this hydrogen, so here, in this diagram, is this methyl group up or down? This methyl group, up, is the top face, isn't it? Okay, so that one, we actually use a wedge, right? Okay, I need to pause this.